that this back EMF, or epsilon L, is directly proportional to the rate of change of flux, which is directly proportional to how much the current is changing. So this guy is directly proportional to how much current is changing. Now the proportionality constant here is inductance, and since it opposes the EMF that is in the circuit, it is called back EMF, and mathematically that just means that you use a negative in front of that right hand side. So that is what epsilon L is. Now there's another way you can get epsilon L, and that is using Faraday's law that I have just said, that it's going to be equal to minus n if there are n number of turns in a coil. Okay, so a loop like this, a single turn loop like this, is same as a circuit like this. Okay, but if you have more turns, so if you have more turns like this, then everything that we studied gets multiplied by capital N. So epsilon L is just minus L d phi over dt. Let's call it B, d phi B over dt. Now using these two equations, you can see that L di over dt is equal to N d phi over dt, or L equals to N times d phi over di. Alright, and this is also true if you, instead of change in flux and change in current, if you could just write down this total flux divided by total current, then this gives you the formula for inductance. Actually, going this way is a little bit confusing, so you can just think of integrating this equation so that you get Li equals N phi, or L equals N phi B over I. So in a loop like this, or in a loop with capital N turns, if you can figure out what the flux is and what is the current, capital I, you just divide flux by current and you multiply the whole thing by number of turns, and that gives you the inductance of the circuit. Now inductance, from let's look at this equation. Okay, from this equation, inductance is also equal to minus epsilon L over di over dt. Okay, and remember, from Ohm's law we know that resistance is equals to V over I, and we know that resistance is the resistance on the current. So the resistor resists the current, right? So the same way here you can see that inductors resists the change in current with respect to time. The way that resistor resists the current, the inductor resists the change in current with respect to time. So as I'll talk about, like how inductor works with a resistance in a circuit, and what happens at different times when you open the switch, when you close the switch, and those kind of things that I'll be discussing in a future video, this will make more sense. What does it actually mean for an inductor to resist the increase in the current? Now SI unit of resistance, SI unit of inductance is called Henry, or capital H, and this is, so 1 Henry is equal to 1 volts per second over ampere.